Everybody say hi, Arlette.
Hi, Arlette.
We miss you. Come back. Enjoy DECA. Do well. Okay, so this is example 3. And I did take some pictures of what this is supposed to look like because that is indeed helpful. If you can actually see the picture, you can visualize what's happening. So example 3, it says the region R in the plane bounded above by the graph of f of x equals 4 cosine. F of x equals 4 cosine of x over 2. Below by the graph of g of x equals e to the x. And on the left by the y-axis is the base of this solid. Okay, so that's the base. So we've got these two functions that kind of intersect, f and g. And in my mind, they look like f kind of goes down like this and g kind of goes up like this. And they're intersecting around the y-axis. Okay, so the intersection includes this point right here, which we'll find in a little bit. That'll be our B. And our A value is going to be bounded right here on the y-axis. So A is 0. Cool? So that's the base shape. That's the base of the solid. It says for this solid, cross-sections perpendicular to the x-axis. So we're cutting them perpendicular to the x-axis. We're cutting them this way, up and down. Cross-sections perpendicular to the x-axis are semicircles. Semicircles. So we've got some kind of a dome shape going on here. So let's not draw it. Let's look at a picture. And please excuse all of my other pictures that are here. Oh. Boo, it didn't send. Okay, pause. I'm going to go get it. Okay, can y'all see this now? Yeah? So you have these semicircles that are chunked out from this solid. Okay? The diameter of each semicircle is this distance from F to G. That's how you measure the diameter across the semicircle, okay? So the formula that we need here whenever we start finding the volume of a solid is we have to figure out what is the area of the cross-section. And I had a kiddo yesterday say, what's a cross-section? Okay? Imagine if you took an orange and you sliced it right down the middle and you opened it up and looked at it. What do you see? 2 circles. Oh my gosh. An orange. No. Like slice it hot dog style, like the across.
Oh, that's sad.
Spheres, right? If you cut a sphere and you open it up and you looked, you would see 2 pieces of circle. Those are cross sections. An orange.
Oh, sorry, I said that one. I was like, that was my wrong.
He's not wrong.
He's not wrong.
Okay.
I wasn't the best.
Imagine if you had an apple and you wanted to see the star. Did y'all ever cut it this way where you could see the star? You cut it in half and you open it up and the seeds make a star.
Like the core makes.
The core makes a star.
I've never known star fruit. I'm gonna get an apple and
Now you know, cut it. Yeah, because if you cut it down the middle, it's lame. You just see 2 apple slices. It's not fun. But if you cut it this way, Karate Kid style, then when you open it up, it's the seeds make a star. Try it. The more you know. Okay, so moving on. That's cross section. Does that make more sense to you? You're looking at the shapes that you got when you cut it. Okay, so area of the cross section here, these cross sections are semicircles. So their area is going to be found by doing 2 pi r squared. Not 2 pi r squared, sorry. Pi r squared, that's area of a circle, divided by 2. That makes it a semicircle. Yeah? Okay. And in this problem, these semicircles are going to be sized differently. How are they sized differently? What does it depend on? the diameter, right? If I cut a semicircle in this little area, it's going to have a really short little diameter. But if I cut the semicircle closer to the y-axis, this is going to be a much larger semicircle, right? And their height, the height of the circle is also going to change as it tapers down because the diameter is changing. The radius is changing. That's how the circle works. Are we cool with that? Okay. We're cutting it perpendicular to the x-axis every time. So that y value is going to fluctuate depending on where x is. So we can get a function for the diameter by doing what? They tell me the diameter is located between here and here. What's going to be the function for my diameter? Close. Look, F is on top. F is on top. It's confusing because of how they wrote it right here. F is on top. So this top function is F, and the bottom function is G. The distance between F and G is the diameter. So the diameter will be found by doing F minus G. Well, that's diameter. What I need in my function up here for A is radius. So we're going to take that diameter and we can divide it by 2. Radius is going to be F of x minus G of x divided by 2. Another way to write that is to call it half F of x minus G of x. Okay, kind of out of room over there. Half of F of x minus G of x. Nope, don't like. Does that feel better? Okay. And so in my area function, that's what we plug in for R. So area for these semicircles is going to be found by taking pi over 2 times half of F of x minus G of x squared. Capiche? We doing okay? We can simplify that a few steps. Area is going to be pi over 2 times, what happens when I square a half? It's a fourth, right? I squared this product. Each piece gets that power. It's not like when I square a binomial. But I square a product, and each piece does get the power. So a half squared is a fourth. And then we're going to have the difference of F of x minus G of x squared. So what's going to be in front of my area function is going to be pi over 8. That is a common factor. When I'm dealing with semicircles, it's really common to see a pi over 8 in front because of how that diameter gets pulled. Okay, so look for that. F of x minus G of x, and the difference is squared. It's, again, this is a binomial. It's not F of x squared minus G of x squared. It's the difference squared. Cool beans? Any questions on how we got to this point? No? Okay, so on the next slide, we'll write out our volume. And we remember that volume is the integral on A to B of the area function. And if I'm cutting these in perpendicular to the x-axis, then I'm using x as my variable. That's the note there. When they tell you you're perpendicular to the y-axis, then you'll have y letters. And so we need to talk about, well, where's B? Where's B? And in just a second, I'll have you put F and G into our grapher. We'll go find B. We know that A is the y-axis. So on 0 to B, our area function was that bottom thing down there, pi over 8. So we can pull that pi over 8 to the very front. Pi over 8 times the difference between F of x and G of x squared dx. And the rest of this you should be able to put in your calculator. You're going to have to find out what B is. That's this intersection right here. So for that intersection, in degrees, for that intersection for B, we should get the number 1 point, I think mine was 937. We should store that for B. Okay, don't ever try to round that. That'll give you the wrong answer.
That was the answer. I got 1.2.
Oh, 1 point, not 937, 1.196. That was mine. Same thing. Don't ever try to round that though. Okay, lesson to the wise. You need to store that number.
Mine just said 1.2.
That's fine.
What was that? The answer in here? 1.9.
And then our final answer here should be 1.937. Get in the habit, guys, while we're working these and we're pulling values from the calculator. Don't round anything until the very end. And at the very end, we should be accurate to 3 decimal places. 3 decimal places. Now, whether you truncate it or whether you round to 3 is up to you. If you're a bad rounder, you should truncate. That means chop it off after 3 numbers. Okay? If you're rounding and you're decent with it, 5 and up, bump it up. Otherwise, keep it. Okay? But we should be accurate within 3 decimals. Any questions on this one? Is that okay? Kind of understand the idea? You've got to take the area of the shape. That's what we've got to see. Got to take the area of the shape. So the base shape is, I wouldn't say is of less importance, but it's kind of not as hard to deal with as the actual shape of the cross section. That's really what we're focusing on. Okay, let's go on to example 4. This is example 4. And I went ahead and put the picture right here. It says the base of a solid S is a circle. That's good. We like circle. So the base is a circle. For this solid, cross sections perpendicular to the x-axis. So again, we're cutting on the x-axis. These cross sections are equilateral triangles. Holy smokes, Batman. Find the volume of this solid. Okay. One important thing about the circle's radius is 1. The circle's radius is 1. Okay, so that should bring up a thought for you. Anytime you see a circle and we're trying to integrate on an interval from the left side of the circle, which would be over here at -1, to the right side, we know that volume is equal to the integral from -1 to 1. But because it's a circle, we could double 0 to 1. That's nice. Good thought. Okay, and if it's a circle, it's symmetric. And if it's centered right there on the y-axis and the x-axis, then you're good to go with symmetry. Now let's talk about those equilateral triangles. Area is an equilateral triangle. That means that its area formula for this cross-section is half the base times the height. Those are going to be changing as what? As the radius changes. As the radius of that circle changes. Can you tell that this circle or this triangle here is standing up on its base? And its base is equal to the radius of the circle, or the diameter, 2 radii, right? Depending on where that triangle is located within the circle, if I drew that triangle down here, it would be a short little triangle. If I drew it right smack dab in the middle, it would be a taller triangle. If I drew that triangle over here on the very end, we have a little triangle. Okay, so that triangle's height and base are going to fluctuate based on the circle and its location within the circle. It's like asking, do you want the heel of the loaf of bread or you want the middle piece? Well, it depends on how hungry you are and how big you want your sandwich. Okay? So it's a function of where it's located. Okay? We can use the Pythagorean situation again. They're telling me in this semicircle picture here that the y value is 1 minus x squared. We saw that a lot yesterday with the triangles that they cut. They would say, okay, if this is the radius r, then y is equal to the square root of 1 minus x squared. Do y'all remember that from yesterday? This is yes, this is Do you remember how we found this y value to be the square root of 1 minus x squared? Okay, cool. So using that information, then I know that the base of my triangle is going to stretch 2 of those. So the base of the triangle is going to be 2y. Because of how they're standing up. It says it's an equilateral triangle with its base along the x-axis. Cool? But now, in our formula over here, we have base. We don't have height. And that brings us to the geometry here. How do I find the height of this triangle? How do I find the height? Well, it's equilateral, which means all angles are 60. If we did an a squared plus b squared plus c squared, or equals c squared situation here, can't even Pythagorean today. That's fine. It'd be wrong.
It's not right. But we can make it 2 right triangles.
We could make it 2 right triangles here. We know that one of the bases, y, is a squared plus square root of 1 minus x squared. Squared would be c squared, the height. Are y'all following this? If it's equilateral, and this is going to get, if it's equilateral, then that means that this width 2y is equal to this width 2y, right? We've just called that c squared. So what if we call that piece, instead of c squared, 2 times 1 minus x squared squared? 2y. If it's equilateral, the 2y that's on the base is also the 2y that's on the hypotenuse. So now we can find a, or the height. So a squared is going to equal, if I square the square root, not equal, a squared plus 1 minus x squared equals 4 times 1 minus x squared. Right? I can subtract this. Let's put parentheses around this so I can treat it like it's a thing, an idea. I can subtract this 1 minus x squared from both sides. And how many of those do I end up with? 4 times 1 minus x squared minus 1 minus x squared. 4 minus 1 would be 3. Otherwise, you could distribute and subtract term by term, but this makes a lot more sense to me. So a squared is equal to 3 1 minus x squareds. Yeah? So a is equal to the square root of 3 times 1 minus x squared. What piece of information is that? Why do we do all of this? That's the height. That's the height of the rectangle. Do y'all recognize this square root of 1 minus x squared business? Have you seen that before? Yeah, it was y. It was y, right? So a is equal to square root 3 y. Square root 3 times y, not the square root of 3 and y. Square root of 3 times y. This is the height. So your area equals base times height. Area equals 1/2 of base was 2y. And height was square root 3y. Well, my half and my 2 cancel. If I simplify that, I get square root 3y squared. Equals square root 3, what's y? The square root of 1 minus x squared squared. When I square the square root, it's gone. So our area here is square root 3 times 1 minus x squared. This is my area function. I've got great news for you. This is the last example we're going to work today. Y'all are not so excited. You are? Brooks is. Are y'all ready to integrate now?
Yep.
Now that we have an area? Are we caught up here? Do you understand where we got those numbers? That's the hardest part. I mean, by far the hardest part. I think this is probably the hardest thing we've done all year long. It's okay? Okay. All right. I'm going to take it. So volume here, we said this is a symmetric circle. So we're integrating 2 times the interval from 0 to 1 of our area function, which was square root 3 times 1 minus x squared dx. You could pull the square root 3. So you could have 2 square root 3 times the integral of 1 minus x squared. Well, what you got? What's the antiderivative of 1? X minus x cubed over 3. And we're going to evaluate on 0 to 1. This is getting nice. There y'all were, lost in the woods. Now we've come to rescue you. It's going to be 1 minus 1/3 minus, open parentheses, big fat 0. Thank you, symmetry. When I distribute this guy, that's going to be 2 square root 3 minus 2 square root 3 over 3. I would love it if I had a common denominator, so I think I'm going to multiply by 3 over 3 on the first. So 6 square root 3 over 3 minus 2 square root 3 over 3 leaves me 4 square root 3 over 3. Wrap it up in a bow. Throw your pencil. Drop the mic. I don't know. Wrap the hooey. It's a little rodeo for, I don't know, whoever. Good? Once you can find the area of the cross section, you're in pretty good shape. You have to know that that area is fluctuating based on where the location is within the solid. Okay, so homework. We got a circuit.
Yeah, I won't be here tomorrow. Can I have this?